or I lose, or I record, or I forgot the geographic information. So here I have space, time, and my variables defined in an explicit way. And when the constraints of geographic information and the constraints of coordinates and the constraints of time. So if I have more than one variable, of course, I can have multidimensional cubes, and here are representing two types of sensors. I would say Sentinel one and Landsat. And here I have the different bands. Sorry, I think somebody, okay. I have different bands. For instance, the infrared bands, the visual bands, the radar bands, if I have. And for each of these multidimensional, I have, of course, latitude, longitude, and time. So also this kind of structure exists, and we can extend the dimensionality for different variables. And just to show you, this is the image where I started my presentation in the first slide, and I like a lot because here that shows us different cubes for different variables, and from Africa in this case. Okay, and why now? Why this didn't appear 20 years ago or 10 years ago? And I think there are two reasons. One is big data, and the second that we also talk a bit is the temporality of this data, but it's also related with big data. In October of 1957, it was launched the Sputnik satellite by the Soviet Union. So that was the first satellite that we sent to the space. But last year, in June 2020, there were more than 6,000 artificial satellites launched. So our space right now looks something like this. And maybe you also heard about the garbage that are in the space and how a new satellite that is sent to space needs to try not to crash on that garbage. So now I think could be more harder to send for that satellites to the space. But this creates a lot of data, a lot of opportunity to observe the data, but also now we have continuous time series of satellite images, at least from 1980. So we have around 4 decades of satellite images. That depends on the satellite and the type of the satellite, but we are having really big data to analyze. And it's not very easy right now to analyze 40 years of data, some of them with daily observations, for instance. And related with this big data, it also appears this cloud computing platform where we can access to the data. For instance, I will just show you a few of them. One is Google Earth Engine, that you can have an account for free. So you need to register, but you can have an account for free. And we can access to different satellite images like Landsat and Sentinel, MODIS, different terrain models or digital elevation model like SRTIM, GTOPO, and others, land cover layers, and a lot of atmospheric and climate variables. So it has, this figure have a few years, but at that point, there were more than 200 public data sets, and it's adding every day, there are new 400 new images, and there are more than 5 petabytes of data. So really, this is a big data, and it's a platform to access this data, but also to analyze on the cloud. So we are analyzing this huge data in Google servers. So that's is really a save of time for us. Another platform is Earth Explorer, and the NASA, well, in this case, is the USGS. So you can access not only data from the United States, but also there are a lot of global data that you can access. You have a search guide, and then you access to the data, and then you can download the data. So this platform is not to analyze on the cloud, but to access, to discover, access, and download the data that you need. And of course, from as an European initiative is Copernicus Hub, where you can access mainly to Sentinel data, that at least for the field that you are involved, the radar layers of Sentinel, I think that might be very interesting for you. So the other points, also all this big data that I was talking about is related because the amount of sensors, the amount of initiatives that are observing the Earth, but also the time components that we have. We have more than 40 years of data. Some of them are half an hourly. So every half an hour we have a new data. That depends on the sensor. Others give us one observation per day, like MODIS, or in the case of Landsat and Sentinel, around once every 2 weeks we have a new observation. So we really need not to analyze as different layers separated from the time continuous, but we really need to put time into our analysis. So now I will talk a bit more of few applications that we can do with this spatial temporal data structure, and they are mainly done by me. So that's because I know very well this, but we can think later in other types of application that you can use or extend this idea. So I will show you some application where even if we had a space-time cube, we choose perform layer per layer because the spatial dimension was more important than the temporal dimension in this case. Another approach where we use it only temporal analysis, but we have the approach if only we analyze one per pixel, we can draw a map from this analysis. And finally, an application where we can perform both analysis together or integrate. And my applications are very related with precipitation. This is a average rainfall rate for the month of March. And why I work with precipitation in Ecuador is because I am here, and we are very in a tropical region, as here is explained a lot, and we have the Pacific influence, but the Amazon influence also. So that is a very important variable in Ecuador, with the strong influence of El Niño and La Niña events. So that's because rainfall is a main variable here. So the first application is to do a downscaling, a spatial downscaling of precipitation. So with departure from precipitation or rainfall satellite images that are quite coarse, because these images, they have 25 kilometers of pixel resolution. So even if that is a very important information for us, we know that we have a shorter spatial variability or an intrapixel variability. So we wanted to have a more detailed, spatially detailed image. So we make this downscaling from 27 kilometers to 5 kilometers using other types of information. Of course, we also use it in situ weather stations to have in situ observations, but we also use it other covariables from satellite like soil humidity, cloudiness, cloud temperature, NDVI, that is a vegetation index. And we analyze it with kriging, that I think maybe you have listened, is a geostatistical interpolation method. So we use it a multivariate because we did this kriging interpolation with several covariables. And we did this in a spatial way. So we, at each time of our time series, we choose one layer and we interpolate it only with the information of that month, I would say. So here is, we have this stack of image with temporal images, but we choose to perform a spatial interpolation. As a second application, we work it with climate teleconnections. So that means that what it, in the way that it rains in Ecuador, it's not only related with local meteorological conditions, but we are under the influence of climate teleconnection. For instance, ENSO, that is the phenomenon that creates El Niño conditions and La Niña conditions. So we use it, the downscaling images from the previous work, and we focus pixel by pixel. So we did mainly these climate teleconnections are formed based on different methods of correlation, and so we perform a correlation analysis of the time series pixel by pixel for different climate or different climatic index that are related, some of them with the Pacific Ocean, but also from the Atlantic and even the Caribbean, that are found to be some relation to the precipitation in Ecuador. As a result of this analysis, we could draw maps and delineate the spatial influence of different climate index. So here in each of these small maps, because one of each maps is showing a climate index, show us the correlation coefficient and the direction and the strength of this the correlation for the different pixels. So here we have one Niño 1, 2, that is one of the indexes is in front of the coast of Ecuador and Peru, that have a huge influence in the Ecuadorian coast region, but also other Niño regions that are more in the East Pacific Ocean also had influences. So even if we were perform a pure temporal analysis, we got as a result a map to see where that influences were. Okay, as a third example of a integrated space and temporal analysis, we perform a spatial temporal clustering. So most of the clustering approaches follow trying to find homogeneous regions on maps, or on the other side, temporal homogeneous regions, but in time. So we use it a spatial functional data. So all our time series we convert it to a functional release. This is a mathematical function. We use it Fourier for that. But and then we measure how a function for the temporal distance in all these functions, but that was weighted with spatial autocorrelation. So we had a temporal, how the similarities, how they perform in temporal dimension, but also in the spatial dimension. And then we performed a hierarchical clustering that was more, I think, more common to find. But the results are spatial regions that have similar behaviors in time. So for one side, we have the regions, the spatial regions, but also temporal similarities that we have in time. And we can find a central curve on these curve distributions for the climatology that best represent this region. So on the one side, we found these big regions for Ecuador that they represent the seasonality of the precipitation. They have similar behavior in seasonality, in which month of the year rain, or in which months are is the dry season. And later we make another layer of clustering in which we find different intensities of precipitation based on the same seasonality. Okay. Well, more applications that are not from my direct work. For instance, maybe you remember that when we have a layer, a raster layer, we perform map algebra. So basically we add different regions of that raster layer. But then this map algebra, that is, I would say, is very easy and very intuitive to do it in one-dimensional, only one layer. We need to think in a box. We need to think in a cube. So this map algebra needs to be extended in order to also perform at least in a three-dimensional space, but many times in multi-dimensional space also. And if you are familiar with Kriging interpolation, we also have a spatial temporal extension to this Kriging, and when we perform Kriging interpolation, what we want to find is a semi-variogram that represents the range, the seal. I don't know if you remember this kind of topic, and then use this variogram to perform the interpolation. But now this variogram will change between time. So we can have per each step time, one variogram, or we can have like this, where I have the distance of the variogram, the colors are the semi-variance, and here I have the time lag. So we also not measure the lag or the spatial autocorrelation between distances, but also between time. And then, of course, the Kriging use this three-dimensional variogram to perform the interpolation, not only in space, but also in time. What kind of tools we can find? Well, I have used mainly in R this kind of data structure. What we have also in Python, now in ArcGIS, there are also some tools to perform or to use these space-time cubes. And if you enter to the help of ArcGIS, there are very nice and very detailed presentation of what the spatial temporal cubes are and how to use them in ArcGIS. And if we are also familiar with the open source line in GIS, for sure you know GDAL. That is a very, very common library because we use it every time that we read different formats of data. We are using the GDAL library. Now GDAL have an extension for GDAL cubes also. And in the row below, we see different platforms. I already talked about Google Earth Engine. Also, I talked about Copernicus Hub, but also we have a Sentinel Hub to access Sentinel image. And I will want to talk of this initiative One is the Open EO, okay, it's a European initiative, and they are trying to make something similar to Google Earth Engine, but for Europe. And also we have in different countries are starting to have the initiative to have this data structure in support of the analysis that needs to be done. So for instance, I know that in Brazil, they have the Brazilian Space-Time Cube. In Mexico, I found information, and of course in, let's say, in Switzerland, in Austria, in Australia, they have a very, they are starting to organize this information in a space science way. And the final objective is to have every time more ready to use data, because the sometimes analyzing remote sensing data is not as easy as we can see. Some data are really ready to use and we can download and immediately use it, but other data needs to be pre-processed, and we need to estimate the variable that we want to use. For instance, if we are interested to know the land cover type, so we need to download, for instance, Landsat image, doing pre-analysis or pre-processing, and then make a, for instance, a supervised classification to get the variable that is of our interest, that is the land cover. Okay, some few applications that then later I would like to talk with you a bit more. So for sure you have more applications in mind. The main applications I give to this kind of approach is to use satellite imagery or images for climate and environmental application. But also you can, if you are monitoring landslide, for instance, with digital elevation model, and even if they are from radar image or you are getting observation in situ, I think this kind of data structure will be very useful for you in the case that you are using drones or unmanned aerial vehicles, the UAVs, for sure, because you will have quite a lot of images of the same area if you are performing monitoring, because you want to see what is changing in that area. And also it's very important to have a structure to store this data. Otherwise, it will store quite a lot of images, and if you don't have an explicit structure for it, would be being a bit messy. And of course, land use changing also needs that change on time. So we need to think how we will store and analyze this temporal dimension. And just to end, I will talk about some technological conclusion in this regard. And first, we have nowadays a lot of spatial temporal data availability, so that is increasing over time. And in 5 years from now on, we will have even more data. This is the data decade. So we have the data now to perform the analysis, but at the same time that make us to face new challenge. And we cannot work only, for instance, in my case, that I'm from geographic information systems and geographic information, I cannot focus only on doing my spatial analysis. I also need to integrate how I manage this big data. So how I manage the volume, the speed, the variability, all these B's that we have in big data. Also, the algorithms and the models to analyze spatial temporal data, they are increasing. So every time we have more algorithms and models to implement. However, there are still a lot of research opportunities. So if you are thinking of you are starting your PhD or your research, think about this, because there are a lot that we still need to do. We need to prepare more our data to be more ready to use data. Otherwise, we are going to be, I think, very few people around the world managing this data, but this data is very important for decision makers, so they can take fast and based on evidence to take their decisions. And also from the spatial temporal analysis, even if we have some algorithms, these two dimensions still need to work to be more integrated. And as third conclusion, from the computational performance, even if the performance of the computational, the computers are increasing, all these processes are very demanding. So sometimes we need to think about integrating high performance computing, distributed computing, or parallel computing, or even thinking in starting to use cloud computing and processing out of our personal computer and starting to use some already available structure. I would say, for instance, Google Earth engine, but also, at least in Ecuador, we have a network of universities that they have a cluster. So we have access, and I know this kind of association exists in different countries of Latin America. So here is called CEDIA, and the Latin America it is called Clara. So, but now I don't remember how is the name in Brazil. But I know that there is this organization in Brazil also. So this is my last, and I want to talk a bit with you which approach we should use, so we can have this data, but still we have the opportunity to choose to perform only spatial analysis, only temporal analysis, or spatial temporal integrative analysis. And I think the approach that you will choose depends on several factors. For instance, the dynamics of the change. If you have your variable that change a lot over time, for sure you will need to think in this temporal analysis. It doesn't change too much on time, but it has a very variable spatial distribution, so we will choose like this. Or if change on time and on space, you will choose the spatial temporal dimension. Of course, the time and the amount of data that is available. In the case that sometimes we know that our variable changed a lot on time, but we cannot have very frequent observations. So for instance, we have once per year an observation. So maybe that makes more sense, even if we realize that we have temporal variability, just to focus on the spatial approach. Of course, in the way, as always, in the way that we decide to define our problem or conceptualize our problem. So in all this, there is a research choice that we make at the end, and that is also based on the research focus that we use for our analysis. So I say that there is never there is only one way, one perfect way to do something. There are different approaches. What we need to do is to make explicit that research choices that we choose, so other researchers or other people that see our work can evaluate, but based on the choice and the conceptualization that we did. So thank you very much for your attention, and we'll stop the presentation so we can talk a bit more. And so first I will try to listen if there's some question. Yes, Chiara?
Thank you,
Yes,
Daniela. I want to thank you very much for your presentation. It was very interesting for me. And I have a question about the management of spatiotemporal data. What's your suggestion about the database to use and so on?
Yes. I have the same the same concern, I have to say, because we can store some raster layers in database, but at least with Postgres that has a PostGIS extension. However, that is not very efficient. Then I know that the Australian Space-Time Cubes initiative, they have some approach and some tools that you can download, and they store in a database that kind of image. But I have to say that I didn't give a try yet. So far I'm storing, I'm not managing a huge amount of data or a huge amount of variables. So I'm storing, yes, in a stack format. Sometimes I use directly R format to make more easy the later analysis, but there are some formats like NCDF that is a multi-layer raster format. So at least you can store or temporal data or different variables in only one file. But I recommend to check the Australian Space-Time Cube initiative, that they have some open source packages, and there are at least one way to store in a database.
Okay, thank you very much. I had the same experience with Postgres. I used it, and yes, my impression was it was slow, not so efficient in that.
Yes, I really have to say that I don't know how this data is stored in, for instance, in Google Earth Engine.
Mm-hmm.
How the data structure that they use to store, because to access to the data and to perform analysis, of course, in their servers is very fast. But sometimes when I want to download the analysis, even if it's a time series at the end, only one time series, so for instance, 10 years, that takes a lot of time. But I think that could be a restriction to only be performing process on their servers and not to download the data.
Okay, thank you very much.
Yes, I have a comment with respect to what you're discussing now about performance. In the database domain, this is a multi-dimensional schema, and data warehouses used to use this kind of schemata in order to address different problems. Then I will have a question on the design of this particular data. But normally, and regarding Postgres and all relational solutions, and also multi-columnar solutions, this kind of systems, the important thing to go fast is to index. So it's not only a question of building the cube, which is already a challenge, but then if you do not create the right indexes, it will certainly, the queries are multidimensional at the end. So you are joining a lot and you are aggregating a lot. So if you do not have the right indexes, it will certainly create overhead in the queries, but this is not a question of, this is not a problem of the DBMS. This is a problem on how you tune the DBMS in order to address this. But there you need someone that knows, I mean, a DBMS administrator that can help you with these indexing problems.
Yes, I think we need to work related to computer science, because this is not only a problem with satellite images, with drones, for instance, that are very heavy images, and if we perform one flight per week, but we can have at the end quite a lot of information. And it's not only a matter of storage, but how we can access
Yes, you need to, you need quick
data.
writes and reads. Yes.
Yes, yes.
Yes. Tomorrow there will be a panel and a colleague of mine, Jose Ramon Diaz Viqueiro, he has been working with geographical data and building data warehouses. And well, he's a database person. So I think that, well, if you have time to attend, we are trying to gather specialists and from different domains, because this event is related to a project. And the project is an action to a coordination action. And we are trying to identify people that could eventually be interested in defining a big project. So, well, I knew you before, so I thought that it would be interesting to contact you. And it is the same with Ramon, who has this other view of the problem, more database related problem. And I think that, well, we have points in common and problems in common to address in an interesting manner.
Of course.
If there are no questions, I have one, particularly with the design of the cube. Normally, when you design the cube, you define the dimensions, and then you define the functions that will let you zoom in and zoom out along the dimensions. For example, in the rain, you showed a very clear example where you aggregate and disaggregate
Yes.
the data. And there, well, normally when you do that, there are sometimes you use functions that can go up in the aggregation, but then coming down, it's difficult. And my question was that, are there functions in this particular data that have this kind of issue?
Yeah, going up is, I would say, it's very easy. For instance, I have daily data, and I can aggregate it monthly. That is very now going down temporarily or spatially. I need to have at least the ways or the approach I follow is to use secondary information that have better spatial resolution, for instance, or better temporal resolution. And so that gives me the intra-pixel variability. But I need to have a relation, so I cannot use something that is not related at all with my variables. So for that, I use co-variables.
But when you start from down to up, this means that you have a disaggregated observation, and then you aggregate and you aggregate. Yep. But doesn't it mean that in order to go back, I know because the intermediate layers, you do not have them, I mean, they are not materialized. I mean, my question is, you need, you have the disaggregated version already, no? But why?
But in a different, yes, I have the disaggregated, but not, for instance, not in precipitation. I have it in, for instance, in soil temperature, because there are layers of MODIS. That is one kind of sensor that it has data at 1 kilometer resolution. And my data is at 20 kilometers. So I use this second layer to trying to get to estimate or to predict how behaves the precipitation based on the for instance, in this case, the soil temperature, the surface temperature.
Okay, so if I understand, you have something, and then when you aggregate to a higher level, this means that you estimate.
Yes, it's an estimation or it's a prediction. So we use a lot of machine learning methods also. Most of the machine learning methods, the problem is that they don't have spatial constraints or even temporal constraints. That is actually, please work on that because it's amazing. I know that, for instance, random forest, there are some initiatives and some approaches to put spatial constraints on the prediction of random forest, but at the end is a kriging, for instance, is the interpolation. They use a regression method, but at the end is a regression that has some sense of the spatial constraint.
Yes, yeah. What I was understanding, is that the intermediate, well, when you aggregate, these aggregations were contained all the information, only that it was aggregated. And what you are saying is that in fact you estimate, you calculate the aggregation, and this is why you do not have enough data in order to go back and out of the estimation reproduce what was the input.
Yes, sometimes, most of the time, we don't have enough data. That is true, but we need to rely on different, for instance, in the case of rainfall, if it rains a lot, it also the vegetation will develop it better. So we can have some information based on vegetation inputs to estimate how is the spatial variability of precipitation.
And do you know at least which is the information that you need? I mean, the complement.
Yes, we know from previous works sometimes, but also we need to explore. So the first part of exploring and to identify that relations is very important, because not in every place, for instance, in Ecuador, that is something that is very interesting to do with this kind of research here. We have the plain coast, we have the Andes, and we have the Amazonian rainforest. So we have the three very different geographic areas, climatic areas, that they behave very different among each other. So we need to explore what are the better variables to use in our prediction in the coast, in the Andes, and in the Amazonian rainforest.
And out of this, you define your, well, the pipeline that will let you estimate. And then to an upper level, what happens? You always need to do the same pipeline?
Can you repeat the question, please?
Yes, in your schema, you have an initial layer, then you have a second layer, and then you have a third level of aggregation. So to go from the lowest to the second one, as you explained, you need to figure out how to compute this aggregation.
Yes.
And then for the next one, again.
Yes, I think you can define how many layers do you want, depend on maybe on the type of data or the processes that you want to make.
Okay, okay. Just to understand what does it mean, because since I see images, I think, well, she has an image and then she aggregates many images and she has another image, but it's not that easy.
Yeah, I could disaggregate as much as possible. However, I need to validate that and to realize that the data and the prediction I am doing, that makes sense and represents the reality. Otherwise, it's not only, I say there are many algorithms, many machine learning methods, but we cannot trust like this on the method. We need to test them and to really know is that. So when we design this kind of experiment, we always reserve part of our data for validation.
Yes, you need assessment every time. And then when you query, well, you already have your cube and now you're going to query. What type of queries do you ask? These are, they are also predictions or they are factual queries?
I say they are more like aggregative.
Okay.
Because I at least I know if this is only my approach, but I would think temporally and spatially. So I need to generate maps. Even if I have 200 maps, I need to show an aggregated map. So or I generate climatology, that is 1 map per month. So I aggregate all the Januaries, all the Februaries.
February.
So I can have at least 12 maps, and that is I can communicate with that. Because with 200 maps, I cannot communicate. Or I choose a point or a region, and I generate the time series that best represents that that region.
Okay. Okay.
So I always present and aggregate on maps or on time series.
On time series. Okay. Thank you.
Thank you. Very nice conversation. I really like it.
Any questions? More? Well, I'd like to ask about the learning curve of using this kind of system. If the user needs a lot of time to effectively deal with this type of system, what do you think about?
Yes, I would say sometimes yes and sometimes no. That I say that depends on the previous knowledge, because some people that have very good knowledge about managing software or even programming in R or in Python. So in that case, I would say using the software would be very easy for them, but maybe they don't have enough experience on geographic information systems, on satellite images. And in that case, what I see that my recommendation is spend few time learning about geographic spatial reference systems. That is very important to understand the coordinates, because this is people from computer science. They need to learn about the data structure and the reference systems that we use, if they are geographic coordinate, latitude and longitude, or they are projected coordinate. That is very important to avoid mistakes. Or if you are so you already know about GIS and all this kind of stuff, then you will need to spend a bit of time learning the software. Now, ArcGIS, I have to say that I haven't tried the tools yet, but could be the easier way to start doing this kind of analysis. So, so that gives to you an interface. But if you are in the field of research, I always recommend using some scripting software, because if not, you are going to be stuck what is already done on the software. So if you want to have some methodological innovation, you need to do it by yourself. Okay,
thank you. We have a question on the chat. Do you know about GIS initiatives address spatial temporal problems with data bases, I think?
Yes.
Data lakes.
Data lakes, in fact?
Yes, data lakes.
Data lake with semantics, about is something related with semantics?
No. Can you hear me?
Yes.
Yeah. So in fact, what happens is that a data lake for some people in the database community is kind of the natural evolution of data warehouses. A data lake, in principle, is a storage place where you put all your data, all that you collect, you put it in raw format. It's like the file system. And rather than spending a lot of time designing the data warehouse, because this strategy, if I remember well, this is a schema on write. The principle in the data warehouse, in the data lakes, is that you read the data, you define the data on the fly, and then you apply the operations that you want on top of that. So it's like time series. We collect time series in waveform. not in I don't know, in another format, or you collect the data and you put it in a special temporal database like I forgot the name of this database, InfluxDB, for instance. And then you have a upper layer based, for instance, on a Spark, which is going to access the data and define the schema and then apply the algorithms that you described. So this is like kind of the new trend in the data warehouse, in the data warehouse community.
I cannot add anything about that, but I will check it because it sounds very, very interesting.
Okay, thank you.
Yes, thank you.
Okay, so thank you so much, Daniela, for being here, for the great presentation.
Thank you to you for the invitation, and I will follow the initiative because I think it's really, really nice what you are doing.
Thank you. Yes, we will certainly keep
Thank
in
you.
touch.
Thank you so much. Okay.
Bye-bye.
Bye-bye.
Bye.
So
Now it's Martin who
have
takes the floor.
some minutes, or the next keynote, it starts right now. We have 15 minutes here in the program.
Yes, we have well, now it's like 10 minutes break so that we can reorganize and go back to the stage.
Okay. So
see you in
later. In 10 minutes.
In 10 minutes, yes.
Okay.
Okay.
Bye-bye.
Bye.
So we have 10 minutes break.
Yes.
While people
we organize. I think that Marcus was having problems to connect, but I don't know if I think that the problem was solved.
Yeah, he's not here yet.
I'm having a look at Slack, and then he said at some point, okay, now I see, and so he normally
perhaps he lives nearby my neighbor. My electricity went down, and just
maybe it is that. Yes, okay.
So perhaps it's a common problem.
In the area.
My internet just arrived back.
Yes. Yeah, maybe it's the area that is having issues. Yes,
okay, so we have about
some minutes to let him. I mean, if he's not here, we can switch the order while he arrives to let him land smoothly.
Minutes.
Yeah.
Okay.
Martín, tus lentes son unos traicioneros.
Ujú.
Hemos estado en los lentes.
No, uno de ellos,
Cuidado.
eh, desistió del curso y el otro tiene clase 8 horas, por lo menos 8 horas de clases por día en la escuela primaria, así que
Qué horror, qué horror.
está todo el tiempo ocupado. En fin.
Ocupado, sí.
Ay,
Issues. Issues.
ya, en fin. Let me share my screen. So, how are the challenges going? I have no news.
Well, we have
anymore.
some good news. Group 1 has been working quite a lot with Augusto. I always say Jose. With Augusto and Javier. I think that challenge 1 is hard, you know, because the data started in a specific format, then Augusto helped to transform them, etc. But anyway, they are having results. I think that the very hard part will be to produce a comprehensive study of the data, which is already nice. And then the third challenge, it's Karen and Placido who have been working with one challenger. He was left alone, but yesterday they worked on Meet with him, and they say that he's doing good work. He's doing processing the images and then getting some results. And the one that I think that people desist from doing it, but I don't know exactly, it's challenge 2. But I'm not sure if they connected independently and they are really working, or that no one is working on challenge 2.
Okay.
Yeah, it's also a good way of measuring, you know, the level of difficulty of the problems and the way people have a look at these problems. No.
Yeah. And also the interaction.
Yes, that's another huge challenge.
I wasn't attending that sort of thing.
Yeah,
I thought
well, a lesson learned is that the subgroups in Zoom are interesting, but as soon as there is too much people, I think that the best thing to do is that the groups are formed and then they try to connect independently and work independently. This gives more room for, you know, liberty to interact. This is what group challenge 3 did. They connected separately and they worked on Meet. I think.
Young people now use Discord and
other tools. So I think that that's a thing to keep in mind. And then, well, the experience is the experience that big companies, data science companies experiment today. I mean, no one is working in the same room and in the same country and in the same schedule. I mean, in Google, in Facebook, and many huge companies really dealing with data science issues, they work online. So this is also an experience to see how does it look like to be a data scientist and a scientist in general in today's new normal.
Yeah, yes.
Considering Group B, we had 2 meetings with Karim, the other guy. For the first day, we had to explain the problem, and we passed 3 activities to him: understand the problem, the data set. As we had PDFs, generate images through the PDF, then process these images. So yesterday we had another meeting with Karim. We have used Google Meet. It was interesting for us. So I believe he's understanding the problem and trying to solve also the problem. Today we had no feedbacks from him. I don't know if we have time, considering the program, to have meeting with the students, maybe not, but we said to Karim to send us a mail if you had any doubts about the code, the problem. So we are in touch with him, he and Karim.
We'll see tomorrow what he manages to do.
I see that today he's not online. Maybe he's trying to solve the problem.
To solve the problem, yes. He didn't sleep. Yes, yeah, tomorrow I think that what people will manage to do is the first part, which is data exploration, which is normal, because this is the hardest part of the pipeline, and people keep saying that this is the most challenging aspect to do when you address this kind of problems.
Especially for problem challenge 1 and 2. No? Challenge 3 is a bit easy. Yeah, but I don't know the other groups. We have feedbacks about the other.
Yeah, the thing is that, as you said, in challenge 1, we have existential problems. Like, what am I doing here?
Existential problems?
Why did I accept this?
That's a good one.
I want to leave.
Yeah, no, but the thing is that, as always, we have raw data, and there are several challenges, like preparing the environment just for reading, opening the file, and understanding what is inside. And then there are also a lot of different problems, like, okay, I know what the data is, then what can I do with that? And finally, there is the problem of computing solving the real challenge. So it takes a lot of time, but I mean, the team is working. There is a lot of discussions. I suppose that at least myself, I have learned some things about geoscience, which is good. And there are some proposals about what can be done with the data. So, I mean, it is a good experience.
Yes, for sure.
Martin, do you think that we contact Marcus to know if he sees a problem?
I only have his email. I don't have another way of communication.
He's on Slack.
Okay.
We are having a look at Slack. let me, someone is asking. Aderson.
I wasn't on slide. Marcos.
Marcos. Well, he's not connected.
Bom dia, maratonistas.
Hola, polifónica.
We are in a real marathon this week.
There are challengers and survivors.
Yes.
We are trying to contact Marcus. In the morning he was having some issues in order to identify the Zoom link. So well, I'm writing him on Slack. Just to inform the audience about what's going to happen next. Now in some seconds, we are going to start with a polyphonic keynote held by Marcus Nunes, by Aderson, Nascimento, and myself, where we will discuss and present our vision about data science and the type of problems that we have been discussing during the event, but also in our interaction on other meetings. And so that will be the first part of the afternoon. And then the third part of the afternoon will be a panel moderated by myself. And then we've been talking a lot about ADAGEO, but we have never said what is ADAGEO. So I'm going to share with you what is ADAGEO and the spirit of it. And then since we are a huge team for this event with coaches, with professors, with the keynotes, and a bunch of people behind this 1 week event. So what I will do is I will interview these people well, I will ask questions, very simple ones, and you can be politically incorrect. You can say these challenges are horrible and very, very challenging. We do not understand anything, and the data is horrible. You can say all this, and we won't get angry with you. We won't invite you the next time, but anyway, this time we won't be angry with you. And yes, our idea is, it's the multidisciplinary, transdisciplinary issue that we have been facing in our project. And then during these weeks, at some point you have the feeling that people are just talking about things that you have never heard about, and they seem very comfortable with these concepts, and you're like, what are they saying? So, well, the idea is to share this because, well, the one thing is theoretically to talk about this kind of interaction, and another thing is to have the hands-on and really try to do something out of the discussion. So that will happen in the third part, which will be a like coffee and tea get together part, where we will have the complaint wall to to discuss about multidisciplinary interaction. So that's what we're going to do, and I'm just giving some minutes to try to see whether Marcus joins or not. Otherwise, I think that we are going to start smoothly, and then since we are three speaking, at some point he can join, and so that we can move forward with the activities.
That's better. He didn't answer me, not on Slack. That's
okay. So yes, let's do that, and then we'll see.
Okay, so let's begin.
Sure. You are the boss now.
Okay. Someone answer me now.
No, it's Jacqueline.
No, it wasn't him. Okay, so people, we are in, then we have already talked about artificial intelligence. We have talked about geophysics. We have talked about data sciences. We have talked about GIS. And now the idea is that we have a kind of a discussion about data science and what we understand for data science. For that, we have three of the researchers on the project, which is Genoveva, Vargas-Solar. She works on database and data science. She comes from the background of distributed databases. Marcus Nunes, also from UFRN, from this university, he is our data science specialist. He is a statistician and data science specialist. And Aderson Nascimento, also from UFRN, he's our main researcher, and he is a researcher on geophysics. So, well, perhaps we can begin. I don't know. Ladies first, Genoveva.
Sorry. Yes, let's begin with data science,
Yes.
and then we move forward. So I'm going to share my screen.
Yes, please.
Share, and then I have to start them. Okay. So I don't remember if in previous talk, I think that someone has already used this slogan. This is the motivating and publicity slogan that explains why do we need data science today. And well, the idea is that due to the evolution of technology and of the capacity that we have now in a democratized manner to collect data from everywhere, from credit card sensors, intelligent devices that we use every day at home, on our personal, on our bodies. So there's a possibility to have a thermometer of reality transformed into data, and giving the possibility to have like a digital twin of reality, a digital representation of some environments where we as human beings move around. And so the slogan says that data is everything and everything is data. In fact, this was said by Pythian, but and this is also related to the idea of datification. If you haven't heard about datification, it is the possibility to transform everything into data. And if you haven't read Homo sapiens from Dr. Harari, I really recommend you to read this book, because there is a very philosophical analysis of the good things and the very dangerous things that can come up if we transform everything into data, and we have this digitalized observation of the world that helps us to do a very profound decision making. And well, there are implications, but today I'm going to stay in Disneyland, and I'm going to talk about promising aspects and technological and scientific aspects of what data is everything and everything is data. And this is, as this said, turning reality phenomena into data, thanks to, in fact, the big data trend that is now an old fashioned term but in fact, it was the beginning of this idea and these new challenges that we are facing through data science. I'm going to start with something that is not quite related to data science, but that is very illustrative of the problem. If you have read Jorge Luis Borges, you have certainly read about this infinite library. And I'm going to start reading some pieces of it. It says, when it was announced that the library contained all the books, the first reaction was unbounded joy. All men felt themselves the possessors of an intact and secret treasure. There was no personal problem, no world problem whose eloquent solution did not exist. Somewhere in some hexagon, I remind you that the library is organized in hexagons. At that period, there was much talk about vindications, books of apology and prophecies that would vindicate for all time the actions of every person in the universe. Thousands of greedy individuals abandoned their sweet native hexagons and rushed downstairs, upstairs, spurred by the vain desire to find their vindication. This is the Library of Babel. Jorge Luis Borges wrote it some years ago. And when I do data science, I have the impression that I'm running across the library trying to figure out whether I find a vindication about myself or other challenges that come up in science. And around this, there are current status and trends. So I'm not the only one who's running around the library trying to figure out how to do with this promising amount of information. And there are two elements that I think can guide us when we want to understand what is the current status and the trends of data science. The first one is not data, it's questions. What are the questions that we want to solve, and which are the data that can help us to answer these questions? But the questions are our guidance. Why? Because questions are less numerous than data. If we go into data without the guidance of questions, we can get lost. So when I'm going to start from, as a computer scientist, from the back level of the stack up to the higher level of the stack. When you have a lot of data, lot meaning whatever it means, 64Ks that got us to the moon, or a terabyte sitting in my iPhone that I have in my purse. So the question is, how are we going to deal with this? Where are we going to store all this data? And there are two elements that guide the way we think about data archival. So which is the kind of library that we are going to build in order to store all this data. The first one has to do with hardware, which are the persistence solutions that will help me deal with huge amounts of data. Huge meaning that go beyond the borders of the current technology. So today, in the hardware domain, people have been analyzing this problem, and they are moving from paper cards to magnetic and solid state. Solid state has become the day-by-day solution. Almost all our machines have solid state disks, and then we're moving into crystal and DNA. So I always say this because I find it incredible. Here in Paris, in Paris 6, people are working with DNA, and in fact, they are using milk to store data. And they believe that some petabytes of data can be stored in a liter of milk. So you don't have to drink the milk, but if you keep it in the refrigerator, you can store a lot of data. Then the problem is to retrieve it. But now, at this level, I'm just thinking about a container capable of receiving huge amounts of data. So that in computer science we call persistence, okay? And then the question is, even if we will have DNA, crystal, or whatever, there are physical limits with respect to this storage. And the second thing that we have to think about with respect to persistence is, for how long will data survive in time? Is all the data necessary to be stored forever and ever? Or can we get rid of some data? Or can we identify some ways of representing data in intention, such that if we need the data, we reproduce the data, but as long as we do not need it, we keep it represented in intention. So permanence is all about how long do I want cold data to live across time. Once I have this underlying solution, then I can go up in the stack and thinking about functional architecture. So which are the data management systems that will help me transparently to deal with persistence, deal with permanence at some level of transparency, okay? And the real question is, which are the data management operations that I need in order to deal with this? At the very beginning of computer science, our data management operations were very light. The challenge was how to bring data from magnet disks into the memory, the heap, the main memory of related to a program. Today, things are much more vast because we need operations in order to order the data, in order to swap the data, in order to fragment the data, in order to distribute them in different disks, in order to aggregate the data, join the data, correlate, a lot of other management operations that come up. And when you do computer science, when you say operation, you think about computing power. Do I have the necessary computing power to perform these operations? And this is where the fourth aspect of my diagram comes up, which are the deployment architectures in which I'm going to run my operations. Do I keep my AI watch? Do I go to the PC center in order to perform these operations? The challenge today is that we need all these. I need to figure out problems and understand problems within the walls of my home, my office, etc. So I need just a controlled version of a lab where I'm going to deal with the data. And then eventually, when I figure out what are my questions, what are the operations that I want to perform on my data, then I can go out of the walls of my lab and try to figure out how to deploy my design in larger contexts. And this is data science. Data science is the methodology that tells me how am I going to deal with all these aspects, and in which moment am I going to deal with this, and who is going to participate in every of the elements of this challenge. So data science is, of course, about mathematics. It is, of course, about statistic, probability, numerical methods, of course, but since all this is going to be applied to data and is going to be executed in on computing systems, the underlying aspect of these sublime representations have to come into the arena and have to be coupled in order to produce usable solutions. Now, if we go and zoom in into data, in fact, I said, well, what we really have to think about is what are the questions that we are going to ask. And if we think about questions, in fact, the type of questions that I can ask on top of data depends on the level of curation that my data have at some point. So in the lower part of my schema, you have the degree of rawness of the data as a spectrum that goes from raw data as the one the challengers are dealing with and have been dealing with during the last 3 days into curated data, which are the data collections that they are going to provide tomorrow. And so this is a spectrum. Then out of this spectrum, I can ask specific questions. If I'm in a raw context, the questions that I can ask are exploratory questions. I want to profile and understand the data. What are these data representing? Are these observations? Are these facts? Are these representations of a mini world? What are the values associated to them? Can I perform a quantitative profiling of the data? And so can I figure out the semantics of the data? Do I have enough insight behind the raw data, some complementary information that can tell me what the data is about? Or am I an expert and in fact this knowledge is in my brain and I can use it in order to explore the data? And then if I move forward into curation, of course, I eventually can have hindsight of the data. What happened if these are observations? Then I can have insight about what I'm observing. Why did it happen? Okay, so all questions that relate to what did it happen are insight questions. And if you have a look at here at my schema, as I move on into these types of questions, my data become less raw. Then I can eventually be ambitious and have foresight of the data. Can I predict something? And then once I have a whole understanding on the data and what it represents, their context, then I get to what we learn, computer scientists, at the very fundamental knowledge of our education, which is now I have a quite curated data collection, and I can have relational queries. I can perform aggregation queries. And for example, the ones that were presented in the previous keynote, there you have really curated data where you can have these relational aggregative queries, or even information retrieval queries, as the ones that we perform every day in Google and other search engines. So, spectrum of querying. The problem here is an existential problem. What are the questions that I want to ask? And sometimes this is the real problem of really using data and running experiments on top of data. What do we really want to know? Anyway, if you go to the strategies that we database people and data science people have in order to deal with the problems, you have to be clear about the type of underlying solution that you are referring to when you ask factual and questions that on top of very curated data, and what are the type of questions that you are going to ask on top of less curated data, according to your objectives. If you are in the right part of the spectrum, that is the easiest part, and there what you will have is data. In fact, what they represent, once they are curated, they in fact represent a mini world. And it contains a set of facts structured according to some data model. There you have the world completely understood. you know the entities of your world, you know how they are related, you know the rules that are associated to them. So in this control representation, you can ask precisely stated queries. I want to know which are the states of Brazil. I want to know how many people, citizens are there organized per region in the country. I want to know how many data collection centers are there installed across the country. These are questions, factual questions that I can ask on top of really curated data. And then what is the result? Well, the result is partial or complete, depending on the database. And if it's not complete, it is always associated to scoring metrics. For example, precision and recall. How precise is this answer, and as to which extent does it respond to your query? Okay, so very controlled situation. If we move forward to not factual, but those questions that facts and aggregations cannot respond, then there we are talking about problems that normally and very often are related to classification. This is why, for example, Mustafa Leba in the first day of the school talked about classification, because that was something that we know since Aristotle. We humans understand the world by classifying. So classification is one of the problems that I cannot, and the queries I cannot solve with factual and aggregative queries. For example, given a set of images of steel sheets, identify those that have wands in a central area. Which are the characteristics of clients willing to buy electric vehicles? Which anomalies cause fatal breakdown in a machine? These kind of things are, these kind of questions are solved by classifying the observations that I get within a data collection. And then there are other queries that are predictive queries. The expected evolution of the market of electric vehicles. The expected active life of a manufacturing machine before its breakdown. Okay, so these are predictive queries, and again, cannot be asked in by factual or aggregative strategies. The problem is that if we want to answer these questions, the pipeline that we have to implement in order to address them looks like this. Just to get into it, first, I have different characteristics of my data. My data, when I want to solve this kind of questions, are observations of phenomena, often described as series of features of attributes. Challenge one for those that are working with it is that you have a set of columns of entities, and you have values associated to them, and this, every record is an observation. Now the queries have this is my iWatch speaking. Queries are have analytics objectives, looks for insights or foresights expressed as pipelines, and they are guided by the conditions and characteristics of the data. And then, very important, the results are models and predictions. Okay, they are not data. And very important, they have associated assessment scores because they are not completely valid. Okay, they are estimations, and so I have to associate them with assessment indexes in order to determine error margin, and they are accepted by comparison. In fact, I am going to produce several, implement several strategies in order to answer them, and I am going to estimate errors, and I'm going to choose the best possible model or prediction that I can produce with different pipelines, with different experiment designs. So normally the pipelines represent experiment design. So I have to run experiments in order to answer these type of questions. And the experiments contain 4 specific groups of tasks: data exploration and preparation, that is accompanied with visualization tasks. Then insight or foresight search, that includes processing and fragmenting the data, training, for example, models, and then validating the results through assessment processes. And the thing is that this is iterative. Okay, so I have to run many experimentations in order to produce results that can cope to a specific quality requirement, and the quality requirement is defined by the group that consumes the results. In order to do all this, that you have, those that are addressing the challenges have seen, I need to have data. And having data is a very challenging thing, because I always use, and my colleagues, my Brazilian colleagues laugh, but I always say orden y progreso. It's the slogan of Brazil, no? Of the Republic. Well, you need that. In order to answer this question, you need to curate and you need order. Okay, so curation and the preparation of the data is a key element in order to run all the experiments that you want. And there you have many different challenges. Of course, you have seen we are dealing with the left part of the spectrum, which is very high rawness of the data. And but these data are used anyway, and they are processed in order to perform experiments. The key here is that all the extra information that are produced during these experiments has to be collected and has to enrich the raw data collection, so that the next ones that will use the data will have information about the conditions of this data. And this iterative process will be called curation, okay? So it's a continuous process in which you enrich the knowledge you can associate to raw data without touching the data. It's just creating more data that describes this data. And it is not only about data, it is also about having information about the experiments that have used this data. Okay, no? So you are building the library. You are building a data collections library with as much information as possible that will guide those that are asking questions to know which data they can use in order to answer their questions. And what do they have to do in order to use it? So now Marcus is here. So there are many different questions that you can ask if you are curating. What are the structural characteristics of the data, the size and the quality in terms of null and missing values, the attributes that can be used in order to answer statistical trends, prediction questions, etc. So different the questions that will guide you on describing the content of your data. Here we come with the data lake. Once you generate all these curative data, curation, for those that do not know, it comes from the art domain. In museums, people, specialists curate the art pieces. Okay, they describe them, they know their provenance, their characteristics, etc. So this is the spirit. And then you have to have the right environments in order to deal with this. And there is today a trend that says that solutions which are called data lakes are good in order to implement such process, because you will let people produce data and archive this data in the data lake, and then this infrastructure will generate the metadata and will maintain the information about the data recurrently in order to create value out of the raw data. So this is how it looks. So you have the loading of the data that are a mess, and then you transform, you replicate, you process the data, and then you create this. And this is ideally what people that are asking questions, either factual or explorative or predictive or classification questions, might use in order to decide which are the right data they can use in order to perform their experiments. I'm not going through the curation workflow because I am monopolizing the stage, but well, there is a curation workflow. There are strategies in order to extract the metadata that can be applied depending on the characteristics of your metadata. And then you can have solutions in order to implement on top of the data lake and on top of different infrastructures, this curation process that will help then other people use and explore the data. Those that are using Kaggle in the challenges are dealing with a data curation space. The data lab of Kaggle, it was introduced, I think, yesterday, and those that are using the challenge or addressing the challenges know that. Well, this is an example of a curation environment of data collections used for experiments, where you have also information associated to the experiments run on top of the data. So this looks in general like this. You have harvesting services, you have data processing services to extract semi-automatically the metadata, then you have representations of it, and then you have exploration solutions so that you can choose your data. And on underlying of that, you have storage services as the ones that I described. Okay, so I'm just finishing. And so what happens in geosciences with respect to that? Well, geodata collections have specific characteristics that are important to consider. For example, you, as we have seen, you have a lot of spatiotemporal modeling data, probabilistic modeling, and this is something that is not very commonly curated. So one of the challenges addressing this specific domain is to figure out what is the right way in order to deal with this type of data collections. Then some of the data are associated with uncertainty quantification. So again, these aspects of the data are not very commonly seen in other domains, so this has to be addressed in a particular way. And then model assessment, prediction, which are the type of queries that might be asked on top of the data collections, could be used as guidance in order to curate the collections. And then, of course, understanding the experiments. So examples of experiments, those that address the challenges this week, know three examples of the type of experiments that someone could expect to run on top of the data. Now, just to conclude, there is the part of curation that requires the Marvel superheroes to come and help us. Because you have in the domain, in the geosciences domain, a lot of data controlled by many different organizations, produced in many different conditions. And the ideal of this library that I started to talk about would be to really figure out a way to build a decentralized library that could give organization to all this data. And there I'm not joking. We need the Marvel heroes to come, because this is huge work. Even if we are talking just about Brazil, it's enormous. You will need to deal with provenance, with content, with experiment description. But out of this, we find here the questions. And I believe that a way to address the problem is being interested only about the questions, which are the type of exploration that the domain requires, which are the experiments, in order to try to build exploration solutions. Okay, just that. If I need to ask this question, which are the data that I should look for, which are the other experiments that have been run, and which are related questions that I can ask for a specific problem. And then if we manage to do this, the second ambition that would be addressable with, with less huge resources would be recommendation. You know, I imagine a student at the beginning of her education trying to discover which are the most famous experiments that have been run in the geophysics area, for example. Can you recommend me these experiments, the way they were set, and the results that were obtained? How were they assessed? How were they profiled? You know, and then use the profile of the consumer. I am an expert, I'm a student, I'm an undergraduate student. Which are the experiments that I can retrieve and study in order to figure out which are the next questions that I can ask? And I think that here we have a lot to do, even if here we are not very organized. So thank you very much. And I am going to leave the floor to the next speaker.
Oh, okay, Genoveva, thank you. I was talking without my microphone. Perhaps we can ask to Aderson to continue, and we refer to questions
Sure.
at the end, or do you prefer to have some questions now?
Genoveva, you are mute, I think.
Sorry, Marcos is here.
Yes,
Okay.
I know. I'm
okay.
talking to him.
Maybe he could, I don't know. It's really, what should be the order? I mean, I really don't know.
Okay, so let's Aderson continue with the talk, and then Marcus is in third.
Okay, guys, let's start. I always like to describe this project, these ideas that we are discussing today, as we are dedicating quite some time already this week to something that normally we do not do a lot in our daily basis. Generally, I'm talking to folk like Marcelo Bianchi, Juan, Augusto, and some other geophysicists or people which I work in my group. And generally, we do not spend a lot of time trying to explain exactly what you do in order to open questions for people from other expertise to come through. So in general, you are very closed, in a very closed, encapsulated space in which sometimes you have the impression that you are doing the best that you can, and you surely want to do this. But sometimes you are in a sea of information and data that make things a bit more complicated, and sometimes your efficiency drops a lot. I mean, Genoveva, I mean, when you mention about the problems with geoscientific database, I would just, you were very precise, and I would just add two other features of geoscientific data. Sometimes actually most of the time in geoscientific data, you're looking for rare phenomena. Okay, it's very common that you are studying such a object or process or events which do not occur all the time in the vastitude of the library that you have. So that's something important to say. And the other thing is to deal with noise, incompleteness, and uncertainty in the data. That's something that we always mention in geoscience. Let me see if I can share my presentation now. As you might see, myself and Genoveva, we did not fetch on what specifically what we are going to talk about, but it's interesting that many of the concepts that she's speaking has a lot to do with things that I'm talking about now. Let me. Can you see my screen now?
Yes.
Okay. Let's see. Okay, that's the. So you've seen this Geoscience for the Future, this poster, and I again invite everyone to have a look at this poster. It's very interesting to see how pervasive geoscience it is. And regarding the questions that we have and where to start, I think Genoveva mentioned about where to start. And I would say a very good start from a database that we already have. So the Brazilian seismographic network is already fully available to anyone in this meeting. So you can download the data, start to play with, and there's a lot to do with this data. And I'm showing you a few examples. So the seismographic network that's where the data come from. The data come from sensors which are coupled to the ground, like here, and this mound here and here. So it measures the ground motion. And the idea is to detect natural and human-induced vibrations. And we think, and Marcelo Bianchi probably can correct me, that we are doing a better job than before, although we have a lot of challenges on how to better, to make the detection of these vibrations more efficient. And the idea is that these vibrations have important consequence especially to hydrocarbon exploration, to the geohazard assessment, and sometimes to defense, to the mining industry. And basically the idea is that if you have such a network like this, you can start to detect vibrations which may be associated with earthquakes, natural earthquakes. And this is important too, because therefore, if you have a good monitoring of the earthquakes, you can run statistical models in certain areas to assess the hazard that you have associated to those seismic events. Though that's a very important data, especially because if you plan to build infrastructure that's going to last for decades or sometimes centuries, you have to have a quantitative assessment on the hazard posed by the geological faults that may imply in some earthquakes that may damage your infrastructure. So that's the basic idea. So I always like, I don't know who said this phrase, but I like it because nowadays it's becoming a motto for compliance. And I know that compliance can be a bit tricky for scientists, but I heard this phrase from this guy that he said that in God we trust, all the others we should monitor. And that's probably true when it comes to environment, when it comes to defense, and probably when it comes to nuclear explosions. We are there is a treaty that has been ratified by many nations that in order to ban nuclear explosions, and seismology is one of the technology used to verify the compliance of the nations to this nuclear test ban treaty that has been put into place by the United Nations. So I'm just giving a few examples that the better you monitor, the better you learn about the country that you have. Another thing that I'm particularly interested is that if you have such a not huge densely, but if you have a dense network of seismographs, you can start to look if the data that you're collecting is telling you something about another kind of observables. For example, here, in this very simple experiment that we made here in Northeast Brazil, we have a seismographic stations in which we managed to transform, or we managed to mimic the vibrations that you measure in this seismographic station inland is associated to the wave height that you have on the sea, the wave height of the oceans, okay? And it would be an interesting exercise would be how this noise at that particular provoked by the sea is being watched, is being seen by the seismographs that we have installed. And the question has a reason for that, because sometimes the reason is the following, because nowadays we have an operating seismographic network for over 10 years. And in 10 years, you might be able to see global or Atlantic Ocean trends on the amount of noise of the data. And the idea is can we actually see that in our data? That's a big, and then you have terabytes of data that's already recorded, and you have terabytes of data that's being produced by all these climate agencies that monitor the sea wave heights in the ocean, on the ocean. That's an interesting aspect of data. Another one is, can we better access these geohazards that we have in our place? I'll show you an example here of a seismic vibration that provoked an earthquake of magnitude nearly 2 in Northeast Brazil. It was a huge rock slide. Oops. So this rock here on the top left corner is represented here by this person. Yeah. So it was a huge rock slide that came up from the top of the hill until the end, and it was picked by the seismographic network. And the idea is, can we detect and can we classify those events so that we have an idea of how often did they occur? Are there any other rock slides that were passed unnoticed in our data set? And I'm trying to stick to Genoveva's rules of making the right questions. And also there is a huge activity, a huge seismic vibrations provoked by quarry blasts, that people explore quarries in this area. Are those quarries compliance? Are they shooting or exploding at the right time? Can we detect them? Can we have an overview map of what's going on in Northeast Brazil in terms of quarry blasts? Can we use those ones which we have already labeled as a template match for detecting other explosions in Northeast in the database that we have? So those are the typical questions that we have. And there's another one, typical one, which we are here in Natal particularly interested. It's our events near Jacobina in Bahia. Jacobina turns out to be a very prolific mining district in Northeast Brazil. So we, in the last 10 years, but 5 years maybe, but there has been reports from the São Paulo University that in the early 2000s, there is a lot of activity near the mining area. So the question is, were those activity active in the last 10 years? Are we able to detect it? Is it somewhat related to the mining conditions? That's a good question that we can ask to our database. And then we come with the challenges, not a comprehensive list that we can start to approach, to go down to actual problems that we have. And I ask at this point if it would be interesting to hear also from Marcelo Bianchi, because he's been deeply involved in the seismographic network, and probably he has other challenges that I have passed it unnoticed to me. How to detect, locate, classifying reports and seismic events using the Brazilian seismographic network. The second question is, can you use the Brazilian seismographic network for climate monitoring and see global trends? Because the sea, it's a very good proxy of what's going on in terms of climate. Can we turn the seismographic network in good proxies for the climate that we are having at the moment and see global trends with the data? Can the data be used in other social, natural contexts? We have to explore this. And because we have a vast amount of data, another challenge that I find very interesting that was brought up by Karen Leopoldino is basically to use an already database that already exists by the National Agency of Petroleum, Natural Gas and Biofuels, and probably get this data, trying to make exercise like the challenge 3 that we used, and then we use this data to be in a platform. We have to think about it and make it usable for reproducible experiments. That's another good question, that we have already access to the data, but I don't think the data from the National Petroleum Agency is curated in such a way that we are able to do the very specific questions. We have to go a bit lower in terms of, I think we have to first organize and put it and curate it in a way that we can make more specific questions that may be useful for some other people. And the final remarks, I did not fetch this with Genoveva. I always like to talk about the Jorge Luis Borges, Two Kings and Two Labyrinths tale. It's basically a tale that the Babylonian kings ordered his subjects to build him a labyrinth that is so confused and so subtle that the most prudent man would not adventure to enter it. And those who did would lose their way. When the Arab king visited his court, the king of Babylon told him to enter the labyrinth in order to mock him. The Arabic king finally got out and told the Babylonian king that in his land he had another labyrinth, and Allah willing, he would see that someday the king of Babylonia made his acquaintance. The Arabic king returned to this land and launched a successful attack on the Babylonian king, finally capturing the Babylonian king. The Arab tied him on a camel and led him to the desert and says that he will now show him his labyrinth, which has no stairways to climb, no door to force, no weary galleries to wander through, nor walls to impede the passage. And then untied the Babylonian king and abandoned him in the middle of the desert, where he died of hunger and thirst. What's the final? Well, there are many ways you can interpret this. And I always like to interpret this the following: is two possible flavors of being lost. If you have no information at all, or if you have too much information and you have especially no management or no particular feedback or no particular help or particular guidance from data scientists on how the data works and not asking the right questions. So that's basically what I want to stop here, and I'm open to questions. Thank you.
Oh, thank you very much, Aderson. And as we see, we have seen a quite different version of quite different interpretation of what data science is from the other point of the spectrum, I dare to say. And now Marcus is going to talk about a more I don't know the adjective, perhaps a more real view of data science from another data science specialist coming from the statistics area. So, Marcus, the floor is yours.
Thank you, Martin. Good morning, everyone. Let me try to share my Zoom doesn't let me share my screen. I need to give some permissions here. I think it's the first time I use Zoom in this computer, so maybe I need to leave the meeting and come back later.
No, try again. Try again. I think that you weren't granted as co-host, and this is the reason why you couldn't share. So now try again, and we can see.
I think should be all right because he appears now as co-host.
Yeah.
Yes. My Mac OS is saying Zoom will not be able to record the contents of your screen until it's quit.
Oh, okay. Okay.
What you can do is, did you use the Zoom on as a program in your computer or as
it's an app
as a web page? You can use it as a web page. You can go out and come in again, and because I'm using a Mac, so I had this problem before. Apparently, the problem goes out if you try to use it as in the web page.
Okay.
Do you see? Because it's
I'll be right back.
Okay. I had this problem too, and it was really weird, Genoveva, because it allowed me to start the first 2 hours with
and then it blocked.
And then it blocked, said I had to leave. And I'm very obedient and I left. And then I came back again from the web browser. And it's working fine so far.
You should have escaped.
Okay. Now you have to put him as co-host.
As co-host, yes.
Okay, I'm here again. Let me try. Okay, you are seeing my screen, right?
Right.
Perfect.
Awesome. So thank you, Martin, for introducing me before, and thank you for the ADAGEO Summit to invite me to talk. So today, I'll talk about data science status and trends and how we can use data science in geophysics. I will not give some examples like Aderson did. I will talk more about the experience I have working with data science in many different fields. So first, I will present myself, who I am. I'll give you a motivation for this talk. And then the main subject of my talk today is data science collaboration. I hope I can tell you how we can collaborate when we work with data science. And then I will finish with the conclusions. So who I am, my name is Marcos Nunes. I am an assistant professor at statistics department here in Federal University of Rio Grande do Norte. I have a PhD in statistics. I got it from Penn State University in 2013. And my three main interests are statistical education. I like to teach statistics to other people and develop new ways to teach statistics. Machine learning. I am one of the first professors here in Brazil to teach machine learning for undergrad in statistics undergrad back in 2015. And I'm very interested in statistical collaboration projects. This is my email, my personal email, marcos@marcosnunes.me, and this is my personal website, marcosnunes.me. It's mostly in Portuguese, so if you don't speak or read in Portuguese, maybe it's not that useful for you, but it's there. And what are these statistical collaboration projects that I'm involved into? I have a lab here in Natal, here, for those who don't know exactly where Natal is located in the world. It's a statistics lab. I was the coordinator during 4 years, and now since last year, I'm the vice coordinator. But it's a lab that offers statistical consulting, and it's free statistical consulting for academics. So many departments and institutes around our university, and even outside our university. Once we had a client from Porto Alegre in Rio Grande do Sul, so it's like 3,000 kilometers apart from Natal. And we are in a network of labs in developing countries. There are 3 labs in Brazil, in Natal, the one I am part, in Teresina, here in Northeast, and in Paraná. So, but there are labs in India, Nigeria, Ethiopia, South Africa, and there's a central coordinator in Boulder, Colorado in United States. And this experience I have in this lab and in this network of labs, I think it's gives me some knowledge to talk about statistical collaboration. So the motivation for this talk is about the interest in data science, because here I went to Google Trends. It's a Google tool. You can give some keywords and see how popular that keyword is in Google search. It's a normalized result. So if you look to the peak of the interest in the word or the keyword, it's normalized to 100. So the peak for data science around the world was at the beginning of 2020 and the mid of 2020, so last year. But you can see the last 10 years, it was a huge growth. So people are interested in data science. People are interested in applying data science to their projects. And this is why I want to talk to you today. How important is collaboration in data science? Because I can't see someone doing good data science without multidisciplinarity. One cannot do a complex data science project alone, unless you are very senior or you are in the field for a long time. It's very hard to work alone, because when we talk about data science for a professional for data science, he or she needs to know statistics, of course, because at least in my opinion, data science is kind of rebranding of the word statistics. Programming, because sometimes your data sets are very huge, especially when you talk about big data. So statistics and programming, they walk side by side when we talk about data analysis. Nobody does data analysis by hand nowadays, but you need to know the area of expertise well. So it doesn't matter if it's a geoscience, if it's finance, you need someone to know well an area of application. So for example, I am good in statistics. I can do some programming in R mostly, but I am not an expert in different areas of application. So this is where I think the collaboration is important, because you have people with real problems, but they don't have statistics or programming knowledge. So they come to us, a person like me, to help them to extract value or extract information from their data. And they can come even before to collect the data, because sampling, it's something very, very important. If you don't sample correctly your data, maybe you cannot have good conclusions about it. So when we talk about data science collaboration or data science workflow, we are talking about usually about this part here, right? This part, the transformation of the data, visualize the data, model the data. This is what we as data scientists, we can do. But we need to know how to communicate these results to our clients or to our collaborators. And sometimes, even in this part, the visualization, the modeling, the transformation of data, the understanding of the problem we have, is not possible to be done only by the data scientists. We need to talk to some expert in the field. And this is a complex task, because you need to put together 2 or more data sets. You need to have sometimes a server to store your data. So it's not something that is easy to do. So it's important to have a good workflow to your data science projects. I think Daniela gave a talk yesterday about reproducible research. And I think this is something we all need to know how to work, because our data science projects, usually they are becoming very complex and very fast. One cannot analyze a data set only in his own personal computer. Usually you need a cluster or you need a server to have your data uploaded to. So have use Git or GitHub. You know, the free version is a good tool to organize the data science collaboration workflow. So you have your main analysis done, but you have like 2 or 3 people or even more collaborating and doing small steps small progresses, and when you add everything together, everyone working a little bit in in different parts of the analysis, you can have something really meaningful at the end. In another reason, because data science collaboration is important, it's because, for example, me, I am a statistician, and I can write code, I can program, but my code is written without optimization. It's not the most, it doesn't have the most performance it can has. So I need a good computer scientist to optimize my code if I need to go to production or something more scalable, for example. Usually I can write code for small data sets, but when you go to a large data set, the performance is not good. So a good computer scientist can solve this problem, but usually they know little about statistics and math. Besides us statisticians and the computer scientists, we have the geoscientists. They have some data expertise, but they usually don't know the statistical tools as good as us statisticians we know. And another good figure we can have in this setup is are the managers or the advisors. If you are talking about academic projects, it's the one who can make these people work together. So you can ask specific things for specific people to make everything work in the end, usually in complex projects. So the data scientist in the end is someone who understands programming more than a traditional statistician. Usually statisticians, they are more used to be only a user of software. They don't write their own optimal code. And so a data scientist has an edge when compared to a statistician regarding programming. And also, the data scientists, they understand statistics more than a traditional computer scientist. So the data scientist, when the data scientist mix statistics and the computer science, he or she can find solutions to problems joining these two areas of knowledge. So it can have something bigger than the two parts. So in conclusion, what I was trying to tell you today is that the biggest barrier for us when we talk about data science and challenges in data science, for me, it's not hardware or software. This is usually is fine. It's easy to get these two things. Communication is the largest barrier here. It's to make a team of people work together and get good results. So we need to use the available tools. So your programming language of choice, Python, R, whatever, and people, geoscientists, statisticians, mathematicians, computer scientists, to maximize our results, to have a good result at the end, a good model or a good analysis of our data. If you want to contact me or ask questions or anything, This is my email, marcus@marcusnunes.me, and my website, marcusnunes.me. So thank you. I hope you enjoy.
Oh, thank you very much, Marcus. Now we have some time for questions. Do you have any questions from the audience?
In fact, I have a question. Well, now I'm the audience because I wasn't.
Yes. Feel free to be the audience.
Yes, I have a question for Marcus. Yesterday, I attended another event, and we were talking about artificial intelligence. And a thing that I am critical about the way it is used, not artificial intelligence itself, is about data preparation. And I have the feeling that all the good practices that we learn in statistics, even if you're not an expert, at the university, we learn statistics. And something that it's very important, for example, is to have a strategy in order to build your data sets, your data samples, and the criteria that you use. And I have the feeling that when people start using artificial intelligence methods, they kind of forget about this, and there is no methodology. My question, you as a statistician that also knows artificial intelligence, why is it? Because it has really nothing to do, or because people are applying the solutions in an empirical manner and with few mathematical knowledge?
Yes, people are applying the tools in an empirical manner, because for us in statistics, sampling is almost everything. You have like two huge steps when you analyze data. First is plan your experiment or your study. And by planning your experiment or your study, it means get first you need to decide, are you doing a census or are you doing a sampling? If you are doing a census, for example, some examples Aderson showed us, they are census. He's collecting every data is available to him. So you don't need to ask about sample size or anything, because he's collecting everything. But when you talk about a sample, you need two things mostly. It's the representative sampling. So if you're talking about people in an election poll, you are talking about people from different genders, races, the scholar level and everything. So, and this is the first thing. The second thing is a sufficient large sample size. And these two things, at least from my point of view, sometimes I see they are not very used by people who claim to use artificial intelligence. So they can make decisions, of course, because you have your data, you put usually in a black box, a random forest, XGBoost, whatever, and then you have a result. But this doesn't mean the output you have is meaningful. So have a good sampling frame is important. You need to plan, you need to have strategy, and sometimes people don't care too much about it. They get the data is available for them, and that's it. I hope I answered your question.
Yes, yes. I was interested about this census. So, okay, so if census, you consider the whole data set.
Yes, it's not in the because you have population census in the countries, right? Because they interview everyone in the country. And in statistics, anytime you get your whole population, it doesn't matter if it's people, it could be a car manufacturer. If I go to Peugeot and get all the cars they made in 1 year, I have the population of cars they made 1 year.
Okay, and you never make assumptions of anything, you use it exactly as it is in order to perform your analysis. Okay. Thank you.
You're welcome.
Genoveva, your question raised another issue that commonly happens in geophysics. There was a time, and still there is a bit, you try to estimate parameters of a model. This is classical problems of geophysics. And then you have people started in the last 20 years to use statistical method like Bayesian approach, which is fine, but it's a bit, it happens a lot, a bit what you mentioned. People sometimes use as a bit of a black box. And even sometimes you go to conferences and you find out people saying that the Bayesian inference is unbiased, fully unbiased, which you know it obviously cannot be, because you have the priors. You have to I'm not a specialist on that, but it's something that it never convinced me. Sometimes people start to apply those ideas and making sometimes very strong generalizations of it's an issue too, I think.
Yes, and I think this is, for example, in challenge one, this is one of the question is assessment. And I think that it's really important that we assess our results, but almost all the process of the solution, and show that and make it part of the interpretation. Another part is the interpretation. That is, I always have the feeling that interpretation is done. I mean, you have the results and you are happy because you have nice graphs and everything, but then the interpretation is not supported by these results. Just people start, figuring out maybe answers that they had already previously, and they just used as comfort the fact that they did a mathematical analysis, but then nothing has to do with anything.
Confirmation bias. You confirm what you want.
Yeah.
Just to add on what Aderson said about the Bayesian bias, if you choose a model for your data, you are biased by definition, because you choose one model. Why don't you choose model A? Why don't you choose model B or C or D? So you are biased by definition. And about the priors in the Bayesian statistics, you need to choose the priors. And your priors could be biased as well. So you have bias everywhere. There's a saying from an old statistician, Sir George Box. He said, quotes, "All models are wrong. Some are useful," end quote.
Yes.
So we just need to find the models that are useful to us. Sometimes can be a linear regression, and it's fine. Sometimes need to be some deep learning, whatever. So I think this is what we have to think about the data and our modeling.
and maybe our focus should be a bit more on the priors itself, rather than sometimes people focus too much on other aspects of the inference. I don't know, I'm just thinking loud. I don't know if you, I'm not a statistician myself, I'm a user, but that's my feeling that I have. We should focus a bit more on priors.
We have to, well, priors are something for the Bayesian. It's in statistics, it's related to Bayesian statistics. But even if you're not doing Bayesian statistics, if you're doing frequency statistics, you need to focus on your hypothesis. So the statistical models work if your hypotheses are respected. So if your hypotheses are not respected, it will not work. For example, something very simple. If I want to model the number of children a couple has, I cannot use a normal distribution because it's not symmetric. You have a curve like this, a peak around 1 or 2, and then something that goes exponentially, goes down exponentially. So, and moreover, a couple cannot have 1.5 kids. On average, of course, in a population, you can have 1.5 kids by couple, but one couple specifically cannot have pi kids or 2.7 kids. So you need a model that can respect this hypothesis about the data. So hypothesis, we need, if we are doing some parametric inference or parametric modeling, you need to respect the hypothesis for the model.
And what about machine learning algorithms? How do we apply machine learning algorithms that are not specifically coming from the statistics? I mean, there are some clustering and another methods that can be used to that. In particular, I remember some time ago, I was in a conference where the person was talking about a model without a model for learning. In this case, was learning trees and learning the schema of a tree without of a tree, a mathematical tree, not a biological tree, without any assumption a priori. They learn from the data, they infer from the data, they infer the most from positive examples, they infer the schema for this data. So this kind of model perhaps may be mixed with models from statistics to somehow balance the information, trying to be less biased, perhaps. I don't know. Also, we are looking now at this moment with a student of mine of a work of a ways to make clusterings not based on statistics but on linear algebra, which are there's this matroid structure that may be helpful. I mean, if we are talking about multidisciplinarity, it's not between big areas, but also the composition of similar methods that perhaps may be useful for well, if we have a big enough team. Okay, I don't know if I'm also thinking loud. Okay, but anyway, and I agree with Marcus for at least in these last few months. The biggest challenge for us was communication. I had well, I have one student that is working with people from at the geophysical department. He is a master student of mine. I had two. One of them dropped out of the course, but the other one, he has he doesn't complain, you know, but he has enormous problems for communicating at the point that he needed to have a personal, not online, but presential meeting with people from the geophysical department to understand what is happening there, to understand the process the data is performed. So we have a lot of challenges, and they are not just technical challenges that we need to address. But of course, I'm talking for me.
You're complaining loud.
Yeah.
Yes, with regards to this choice of models and strategy, I wonder whether, for example, in the statistics domain, have you identified whether some of the problems that are addressed today by artificial intelligence can be addressed through statistical methods, or, I mean, clear mathematical methods, and not with artificial intelligence, or rather than with artificial intelligence?
Genoveva, I think your question, just to, sorry, I want just to complement, because sometimes artificial intelligence at least became a kind of fetish word that people use it, and sometimes you're not really sure what's behind it. And I see a lot of this in geoscience, to be honest.
If you let me share my screen here, so I can answer the Aderson, Genoveva, and Martin. This paper here is from 2001, from Liu Breiman, and it's titled Statistical Modeling the Two Cultures. I'll show you just the first page, because in this paper, he has, he presents for the first time two schools of thoughts that could be used to model data. One is the one from statistics, the traditional one, when you have something like your response variable and your predictor variables. So you want to say how Y behaves based on X given a model. So it could be linear regression, logistic regression, Cox model, whatever. And he presents a second way of thought, the algorithmic modeling culture from computer science. So this is exactly what Martin said he saw in a Congress, in the event we went. Decision trees. You have your prediction variables, then you have a black box algorithm, and then you have your answers. So you have these two schools of thoughts today, and sometimes you cannot solve problems using the more traditional way. I'm not against the algorithmic modeling culture, but I prefer to use this first one because it's related to the hypothesis about your data, is related to look to your model after it's fitted, and you have more information to say if it's a good fit or not. You can go with more sophisticated tools than only, for example, cross-validation. You can do something more interesting. And the problems you cannot solve with the data modeling culture, I usually go for the algorithmic modeling culture. But the problem is something Aderson said. I don't know if we have this expression in other languages, but in Portuguese, we have a saying that is something like, if you only know a hammer, every problem for you is a nail. So if you only know black box techniques, you use them for everything. And you have a result, but it doesn't mean it's the best result you can have. And other thing Martin said was about clustering, not based on statistics. Cluster is a very, very hard task to do because you don't have your response variable. You know you want to split your data into K groups, but you don't know what's the K number. So clustering it's very hard. You have many algorithms. K means you have KNN, you have DB-scan, and then inside the algorithms, you need to choose a distance, Euclidean distance, Manhattan distance, and so on. So this is, I think that the best way to solve this is to talk to people from different areas. So someone has a problem, and so from geoscience has a problem, he talks to a statistician. The statistician cannot solve alone. He has to talk to someone from computer science. And then we go to the biggest problem that I think Martin agrees with me, like he said before, communication. Sometimes 2 people or 3 people are talking about the same thing, but they use different words and nobody understands nobody.
Yeah. So I don't know if there's more questions from the audience.
I think that well, the next part is to talk about exactly the visions that we have had through the project and also through the week in which we have been working like on problems. Even the definition of the problem has been a challenge itself. So for the audience that are challengers and that are working with people with addressing the challenges, and people students that are addressing the challenges, an important thing that you have to do is that defining the problem was a challenge itself, exactly because of the problem of different cultures coming together to state a problem. I will give you an example. Aderson said, and his group said, oh yes, we have the data. And and suddenly, okay, where is the data? And yes, don't worry, we have the data, and we open some Google Spaces in order to store the data, etc. And at some point, almost a day before the event, I get an email from one of our colleagues with the data attached to the email. And I was really laughing, because we were expecting, the data collection and a process, an FTP process, very complex. And we had the data in the, so this was like a shock. And then because we have PDFs, and one of a common question in the challenges was exactly to have a quantitative description and profile of the data. Normally, for example, when I teach data science, I tell students to go back to their statistics courses and refer to descriptive statistics metrics in order to profile the data. And suddenly we had PDFs, and another collection was proprietary data to be transformed. So yes, of course, we are talking about data collections, but our understanding and expectation about data collections is not at all the same.
It's interesting that you mentioned that, because if you may ask, when we had myself and Bruno, we were working together in a project to parallelize a very intensive way of solving a problem. And we had also these problems of data. I'm recalling now, because in geophysics culture, you never, and I have to say, I was a bit surprised with the data. We never approach the data as a we know that at the end of the day, in the computer memory is a table. It's tabular. We know that it has to be, because I always joke with the students that a geophysicist, you're probably a better geophysicist if you know linear algebra rather than calculus, because at the end of the day, everything is linear algebra. And I don't remember, and maybe other geophysicists we don't remember the last time we saw a CSV file from a data stream. Because it normally goes into this, you may say, weird or proprietary or whatever format. Everything is binary, although we know at the end. So you can clearly see that it's just a matter of definition what data is, and this makes a lot of confusion. That's true. And the other thing is to do with, Mustafa's very first lecture was very enlightening to me too, because at the end of the day, a critical point on machine learning is clustering. Yeah, that's if you want to leave the message for anyone that's learning how to do this, wants to study machine learning, clustering is the critical role. And after he said that, everything became a bit clear, because it was a concept that I was a bit more, at least intuitively, a bit more familiar with. And sometimes just you have one or two slides that you say, oh, that's what he's talking about, and it gets but those things are more than normal to happen in different communities. And I think that at least for what it means data and clustering, I'm a bit better now.
Then questions, and that's you will be complete. But then comes Marcus with hypothesis, and he kills everything.
We have a saying in the geophysical community that says the worst thing that you can do as a geophysicist is to fool the geologist with physics and to fool the physicist with geology. We have to now to add another community, which is data scientists, because in order to fully bond, you have really to speak the same language and not avoiding every kind of jargon or every kind of sometimes some attachments to the language that you use.
Yes, I think that the advantage, for example, there's a variety of the community of data science is very diverse. We have people coming from mathematics, very formal way of thinking. And we have, as you have shown, the computer science community with more ole ole no approach. we want to code, you know. I mean, we want to have algorithms, we want to code, we want to have parameters, and then the thing runs, and we are happy because it's running, and then we deploy it on a high performance computing backend, and now we are more happy because we have a lot of data, and you know, this is the way the community feels comfortable, you know. And the thing is that, well, I would say that geophysicists are users now of this expertise, very diverse expertise. And it is also important to know who you are stating the problem to, you know, because different communities will ask different questions, even for the data, you know. So the expectations about the quality of the data are always are also very different. And this is the hard, I think, the hard part of the situation too. And we have also the same perception. At the beginning, you talked about geosciences, then there was science of the earth, and then there was geophysics, and when I was trying to address people, you know, to explain, then I thought, well, who am I talking to? What is this? What is the discipline? I am kind of lost. I have the feeling that I'm using the wrong vocabulary all the time, you know. People know that I'm out of the domain completely. You know, so this is
but Genoveva, I mean, it's a feeling that sometimes myself I have too, because most of the work I've been doing here in Natal, it's with people which are known geophysicists most of the time. So and it's always a bit like this, because it's sometimes very hard to draw a line of, you know, some people consider yeah, some people, depends who you ask, people will say, oh, Aderson is a seismologist. Some people say, no, he works with this other guy from geology, so he should know some geology, which I don't. Very basic things and very, very instrumental things. So it's sometimes very hard to address those labels, in my opinion. And so that's why I felt very comfortable to engage in a bunch of ideas of data science with a bunch of people that I didn't know, because you know, I knew that at the end we would come up with something more solid, and it takes time. We have to be patient, and it takes, you have to insist, and you have to you know, it's always like this. It's always like this.
I would like to if people who are addressing the challenges are not comfortable, I will not directly address to you, but I would like to touch an important aspect with respect to education. If we see students' profiles, we can see that, for example, well, I have the feeling that in geophysics, because of the type of problems you are addressing, your mathematical background is solid, and you keep, I mean, for example, many computer scientists come having engineering background. And this means that at the very initial part of your studies. Of course, you learn linear algebra, etc. No, so, but then as time goes by, and particularly when you start master, etc., you as at least, well, if you are addressing like artificial intelligence, algorithmics, maybe you still use this mathematical knowledge, but if not, you tend to forget. So I have the feeling that our students' mathematical background diminishes. And then if we would like to imagine that in the project, we say, okay, let's profile experts that can be in the interface, you see, that can address geophysics problems, but also the data science perspective with computer science skills. What would be the basic core that you think we could propose to these people?
Wow, that's a big challenge because it's a problem that we still have running a program in geophysics. There is always a big discussion on what should be the profile of the outcome of a student. 10 years ago, when I was deeply involved in formatting the undergrad degree that we had here, we wanted to give the student a broad view of geoscience with mathematics, some methods, geophysical methods, and also that the student had computer literacy, which means that the student has an algorithmic thinking. Of course, that's something that you idealized, and then comes reality when you implement things. Because in order to do your ideal undergrad program, the only way to do it is if you were the only person lecturing it. So you do it as you think. Reality is very far away from that. It comes to issues that sometimes the material that's taught in a specific method or in a specific component of math has nothing or not a lot of adherence to what the reality of the student is. For example, when you're learning calculus, or when you're dealing with calculus, or even when you're dealing with linear algebra, at least at my days, very few people explain that's how the computer works. That's how, and sometimes when I am talking about signal processing for my students, I always go to the discrete math and how things actually work. And sometimes I find it really surprising that the students have a strong difficulty on thinking about in summations rather than integrals. And some of the results are very surprising for them. And so it's something that is missed, and I really don't know how to trace it. So therefore, a good student with this profile is a student that is ready to adapt, that's ready to learn different things and to adapt to it. It has to leave the comfort zone, because the student has to know a little, has to is the guy responsible for making these links from someone from computer science and from someone from geophysics. Because sometimes the geophysicists, and that's a problem too, another problem too, sees the computer component as a black box. So he doesn't really know exactly what's going on inside there. It's something a bit more abstract. But if you get someone with the profile of trying to make those bonds, that's the perfect student that can be shaped to because this student is not going to be a computer scientist fully. It's not going to be a pure breed geophysicist because he's, but what exactly does it mean to be a pure breed computer scientist? It's the way we label things at the end has a lot of implications on the way we do the formations of these students. And I think we have somewhat to starting to break those chains, because it's not good, and it only makes you go digger into your own backyard. That's the general perspective that I have. And I would say, just to finish, a student with a good knowledge on linear algebra and knowledge on the physical process behind it, it will definitely succeed on a kind of on these kinds of challenge that I've shown you. Because some of the challenge that I've put there, not even myself know how to properly address it. I know that the Arara is speaking, but I don't know where it is.
Well, that's why they are called challenges.
Yes, exactly. I have just a broad view of what it should look like at the end, but
yeah, in general, I really agree with you, Aderson. We are part of the problem because I feel in our students, for instance, in my course this semester, it's a very practical course, but our students, I feel that they are interested only in solving the problem. They are not interested in learning this, why they are solving the problem with what's happening with the solution, and it's like a formal attitude in this matter. They love to have a problem which is solved. And I said, I'm sorry, but you are not here to touch the keyboard. You are here first to think and write in the paper, and then to implement the solution that you created. But that's a very, very difficult thing for them. And we are part of the problem we form them like that. Like in mathematics, they love to know how to solve certain integrals or derivatives, or say I don't want what, but they don't understand how it's working that thing or why. And I think that this comes from the humanistic nature of at least Brazilian education. You don't see that, for instance, people from the School of Music to learning the physics of the chords of the violoncello, for instance. So we are part of the problem, and we need to be part of the solution.
I don't know if, for example, coaches or students that are still connected now can share your impressions about how you felt about the problem when you saw, for example, the challenges, etc. Did you feel that you were short, for example, in mathematics? For example, the first challenge where you have to figure out a geometric solution. So were you short in that, or did you feel that you were short maybe on how to go from the specification, the mathematical specification, back to a computing solution, or how to correlate data with the solution? Where were the points in which you said, oh gosh, what am I going to do?
I don't know.
Well,
Anyone
I'm
for the
going to
challenges?
share before we kind of I don't know if there's someone.
Genoveva,
I
let
know
me
that
just,
you.
yeah,
Yes.
no, something before. I don't know, is Marcelo Bianchi there? Can he hear me?
Yeah, I'm here, Aderson.
Yes. Do you have the same feeling at São Paulo University with the students, that this kind of difficulties that we are facing? Or
Yeah, I have it, and I kind of agree with some aspects that you put. I think we are really the cause of the problem, and we need to find a solution to that, but we are not alone the cause. My main view is that we receive students that they pass it through a system in school that teach them to search for answers and not to question. And so when they came to university, the only question that they can do is ask for solutions. And this is a major thing that I see a lot, and the students are not motivated. I think there's a motivational part, but sometime or in some time of their life, they have been denied of questioning probably the right answer, and when they come to university, they lack. And the computational issue, I think, it's actually from my side, I see that when we are in the geophysics, the students, they have different views of their advisor. Like there are the guy that program Fortran, there are the guy that program MATLAB, there is the guy that does C, and the other that does Python. And there is a large resistance from geophysicists to switch technology. But the computer science is moving and the languages move together. Like we are doing is still procedure programming, and the community outside, it has object-oriented or interface programming that our students don't benefit from. They have a very hard issue of abstracting the problem because they are too tied to the tools that they use as reference also.
Yes.
And us as researchers and professors or tutors, we are too busy to adapt. And I think that sometimes if I don't listen to my students, I get behind. And probably the next students that come, I will not be able to show them how to better benefit for what's coming. I think, I don't know, maybe that's a little what I see.
You basically portrayed me, because because I have this difficulty, and it was very enlightening for me to have the talk, well, yesterday or before yesterday, from Javier, where he shown us many different ways that you can start to learn to move on towards those aspects that you were saying. I mean, I don't want to overstate it, but it was Javier, are you there? It was a very touchy.
Yes, I'm here.
Presentation. It was a very touchy presentation for me. You know,
Thank you.
I felt called that I had to move on. You know, and it made me think about a lot of the different aspects on how I conduct my research. And I'm very glad for that. I'm very glad for that.
And it's nice to see that the Javier presentation. Also, I see parts of it, but I see that some students that I have, some of them, they bring these tools to me. And sometimes I feel that I just let it pass. you know, and I didn't pay the attention I should give to the student when he showed me that. And I say, no, come on, maybe we should do this way that I know that it works, that it's okay. And I let the tool pass it. And then I feel that sometimes we need to pay more attention probably to all that.
Precisely that. I felt myself in the same situation, yeah.
Yeah, well,
sorry,
just
this is looking like a therapy session, but I don't I don't want to how to say, to patronize on the conversation here. I'm sorry.
Well, just in order to answer Genoveva's question, I wasn't here at the beginning. Yesterday, well, working with the team, I mean, in the team, there are two different profiles. We have one person specialized in sciences, which is good. And the second one, she's more in the machine learning area, computer science, but kind of in the middle. One of the things that I saw is that even having people with the different perspective that were supposed to be together for the challenge, we still face some, well, they had problems in order to address the problem. I mean, even if it was technical, the skills required for dealing the problem, I mean, it was evident that they need some help, but from the bottom up in order to propose things. And I suppose hearing you, it's funny because I've been working with the computational social sciences community for quite 2 or 3 years. And it is exactly the same. People from the social sciences domain and even the humanities, today with the digital humanities, they already identify the problems. They know that computer and computer techniques are a kind of a solution, but now they are working in providing tools and the theoretical material to the students so that they can address this type of problems. And it's my impression that it is something that has to be established in this discipline too. Well, just to finish, yesterday I was reading because there were some access to questions during the challenge. So I started reading about the library, the OpSpy, yeah, library, and I understood. Now I understand what the challenge is, what has to be done, and so on. But I mean, I have quite 15 years of experience, right? So it's a kind of we need to identify what the students need to learn in order to at least enunciate the problem and ask for help to the right person.
So we have a lot of things to do with our research, with the students, with education. And this is good news because we are not out of work. So I don't know if someone wants to add something. I think that we are reaching the end of the day. And I thank you very much for interacting. The interaction is always very enlightening because we have like mirrors to see, to watch ourselves in different conditions, and this is also important for everyone, I believe. So we are going to close the session now, and looking forward to tomorrow's panel, where we will have Marcelo, and with with our teasing questions. And so we will have that, and we will see the results of the challenges, which will be also very interesting for everyone to see how people address the problems and what type of solutions they came up with. So thank you very much for today's interaction. I wish you a nice end of the day wherever you are in the world, and looking forward to see you tomorrow.
Thank you, everyone. See you tomorrow.
See you.